Hi, everybody. Welcome back to Dave's Math channel. This is kind of my continuing feature on the Math Lovers book. And yesterday I started talking about functions as part of sequential programming, which is section 8.4, chapter 8, which is on computation. And today I'm going to talk about a very powerful technique regarding functions known as recursion. So anyway, let's begin. So what is recursion? Recursion is just when you have a function that calls itself. That's so a good example of that, usually the first example people learn when they learn about recursion is the factorial function. And I talked about the factorial function when I was talking about combinatorics, I think. I don't remember which chapter that was. Oh yeah, it was group theory. So you probably remember that n factorial, n is supposed to be a non-negative integer. N factorial is just the product of all the numbers from 1 to n. So for instance, 5 factorial would be 5 times 4 times 3 times 2 times 1, which turns out to be 120. And the factorial function is a good example of a function that can be defined recursively. I think I also mentioned that 0 factorial is defined to be equal to 1. That's a little bit of a strange definition because you're not multiplying anything when you come up with 0 factorial. You're multiplying all the numbers from 1 to n. Well, 0 is already less than 1. So how can 0 factorial even be defined? Well, it's really an empty product. And an empty product kind of by convention is equal to 1. You're just multiplying nothing. And you kind of start with 1 when you're multiplying a bunch of stuff. That's one way to think about it. Another way to think about it is we have this recursive definition of a factorial function. Whenever you have a recursive definition, you always have to have at least one base case. And so you can look at the base case in the case of n factorial is n equals 0. That's the smallest integer for which n factorial is defined, and we're defining 0 factorial to be equal to 1. So you can just think of that as a definition if you like. It might look a little strange, but now if you want to define the factorial of a bigger number, a positive integer, it's just defined to be n times n minus 1 quantity factorial. This is called a recursive definition. So for instance, 1 factorial by this definition is equal to 1 times 0 factorial, because 0 is 1 minus 1. We already defined 0 factorial to be equal to 1, so it's just 1 times 1 or 1. So you can see that 1 factorial is going to be 1. What about 2 factorial? Well, 2 factorial is 2 times 1 factorial. We already calculated 1 factorial. That was 1. So that gives you 2 times 1 or 2. And you can keep going this way. And just to give you a more complicated example, what about 5 factorial? Well, here's how we would compute 5 factorial using this recursive definition. When it was 5 times 4 factorial, now you have to compute 4 factorial using the same definition. 4 factorial is 4 times 3 factorial. I think you can see what happens here. The factorials keep expanding out from this definition. Finally, you get 5 times 4 times 3 times 2 times 1 times 0 factorial, but we already defined 0 factorial. That was our base case. So we're finally going to get 5 times 4 times 3 times 2 times 1 times 1, which is 120. And when the computer does this, it multiplies things one step at a time. But anyway, that's what you get. So that's how recursive functions work. And factorial, just a really good example of a function you probably want to define recursively. And it's very efficient too. Computers can do this very quickly. And in the case of 5 factorial, it takes a total of like 6 steps. In general, n factorial is going to take n plus 1 steps. It's just this n plus 1 multiplications plus, reference to the base case. 0 factorial is 1. Here's how the code would look for computing a factorial. So we remember how we define functions, and this is basically C, but I'm calling it pseudocode. So you have this function called factorial, and the input has a single input, a non-negative integer n, and it also has a single output, the factorial of n. So the first thing we do is we check the base case. We say if n is equal to 0, return 1. And then if it's not the base case, if n is bigger than 0, then we say n factorial is n times n minus 1 factorial. And it's going to keep repeating that until it knows how to calculate n minus 1 factorial. Once it gets to the argument 0, it knows that's equal to 1. So that's how it works. Anyway, so that's how the code looks for defining a recursive function like the factorial function. And I thought I might just give one more example. This is a little bit of a more complicated example. Another very important example. These are Fibonacci numbers. So Fibonacci numbers are also defined recursively. We say that, and we define them for non-negative integer indices, f sub n, the nth Fibonacci number. We say f sub 0 is 0, and f sub 1 is 1. We actually have two base cases for the Fibonacci numbers. And then if n is bigger than 1, we say f sub n is equal to f sub n minus 1 plus f sub n minus 2. This is the sum of the two previous Fibonacci numbers. So that's a recursive definition of the Fibonacci sequence, and we can write code to compute the Fibonacci numbers this way. Yeah, I didn't show you the code. I think I'm not even sure if I put it in my book, but here's how it would look if you calculate, say, f sub 5. So f sub 5 is f sub 4 plus f sub 3. Turns out this isn't a very efficient way to compute Fibonacci numbers. There's a better way involving arrays, which I'll get to next time. But so now we have f sub 4 plus f sub 3. We have to do f sub 4 and f sub 3 again. F sub 4 is f sub 3 plus f sub 2. So 3 is f sub 2 plus f sub 1. And then we just keep simplifying the Fibonacci numbers until we get to a base case. So f sub 3 is f sub 2 plus f sub 1. I think I did a little simplification here. I just put the two f sub 2's together. So we get f sub 2 plus f sub 1 plus 2 times f sub 1 plus f sub 0 plus 1. We already know what f sub 1 and f sub 0 are. So we're going to get f sub 2 is f sub 1 plus f sub 0. And then f sub 1 is 1 by definition. And we have 2 times 1 plus 0 plus 1. So 1 is 1, f sub 0 is 0. So we plug everything in. Finally, when we simplify everything, we get 5. That was a lot of calculations just to get f sub 5. And like I said, it's not a very efficient way to compute Fibonacci numbers, but it does work. And I'll show you a more efficient way to do it next time. But anyway, that concludes my video for tonight on recursion. Thank you for watching. Long live math. And I'll see you guys next time. Bye.